これさっき魚富でもらって行ってみましょう。カラオケボックスでもあればな。
So the blue area is the region where all our models lay. They have these J4 and J6 parameters. These ones here, the green ones, are results of Nadine Neckermann, because we are not the only ones doing these interior calculations, of course. And these ones here are results from both Carniviter and Bill Hubbard. So we are all more or less on the same page regarding the J6. We do not agree so much in the J4. And the question was, of course, these models have a completely different structure for the interior, completely different distribution of the heavy elements, completely different mass of heavy elements, core, no core. So which ones of these are actually correct? And if you see these points that we have here, they have large error bars. This one also. This one is completely off all the models. So we were wondering, okay, what's wrong here? Are the observations or are all models we are doing the right, we are considering the right part, the wrong parameters? So that's where Juno came and we saw us for this, because this is the Juno point that we got after the first orbit. So with only one orbit of Juno, and again, one orbit only, we got that point. And the error bars are really small. When we saw it, was like, oh wow, this is so great. And this is, of course, we had like two independent teams doing these measurements, and they were discussing a lot about the error bars, which ones to put, which ones not, and they decided to put the larger ones that they could. So these are really the larger error bars we put there. The one in J6 is inside the dot. So it's really, really, really good measurements. And of course, this helped us with the models, because then we knew where the models were. Now we have to understand which are the models actually fit this data with so incredible small error bars. So one key parameter I said at the beginning is the equation of state. And this is something that we still don't know, I'm afraid. Even for hydrogen, that is the more the simplest element, we have different equations of state, and they are giving different results. So here I split all our solutions into two different equations of state that we were using. And it was very fascinating. So, okay, with this equation of state, we could find solutions just, but we couldn't with this one. So then this was a very good question that we had, why we cannot find solutions with that equation of state. So we start looking at who are really the key parameters, what changes in all these points, in all these different solutions. And after checking a lot, we found that the very key parameter besides the equation of state is the distribution of heavy elements in the interior. So when we have that Jupiter is completely homogeneous, that everything is well mixed in the interior, then we are close to here. This means this zero here, because this is the difference in heavy elements between the atmosphere and the interior. So if everything is well mixed, we are here, very far away from the measurements. But when we start separating this, when we started putting more heavy elements in the interior and less in the atmosphere, then we started getting closer and closer to Juno. So Jupiter is not homogeneous, as we thought. We really need to have a difference. We need to have more heavy elements in the interior of the planet. And then we start working with these other equation of state, because we wanted to know if it was not possible at all, if it was a problem of the equation of state, or if it was a problem of the models that we were considering. And what we found is that if we have this classical model where we have a small core and these two layers, when we put more heavy elements here, we are actually getting closer and closer and closer to Juno. And we were able also to find solutions with this other equation of state, with this other model. So we are proposing these two models for the interior of Jupiter that actually match the observational constraints that we have so far. With this one, which is the classical model I showed you at the beginning, we have this layer of molecular hydrogen, of this helium that is dissipated. We have this layer here of the helium ring. We have here metallic hydrogen, helium. We have a core. And with this one, we are able to find solutions using this equation of state. When we are going to this other model, we are actually able to find solutions with those equation of state. So this is my favorite. That doesn't mean that this is not possible as well, and there is a problem with the calculations. But these other models, we have molecular hydrogen and helium. We have this region of helium ring. And here again, molecular metallic hydrogen and helium. We have a core. And we also have this region that we call music core. So this is actually a region that has a lot of heavy elements, but they are mixed with the hydrogen and helium envelope. So these are the two models that are giving us good solutions to match the observational constraints. It's not possible to find solutions with no core at all. Jupiter is not homogeneous. We need to have more heavy elements in the interior of the planet. Now, of course, it's a matter of definition of what we call a core. So if all this thing is a core, including this part that is mixed with the envelope, or if we just call a core the distinctive part where we have only heavy elements. But really, we need to have this core. We really need to have a larger amount of heavy elements in the interior of the planet. So this is really cool. Now we know more about the interior of Jupiter. We know more, and now we need to start asking other questions to understand the formation, of course, of the planet. And that's really what's next. So for the second part of my talk, I'm going to be talking about the rotation of the planet. And this is really, really exciting news, and I'm going to be showing results of three Nature papers. So please don't post it on Twitter or Facebook, because they are not published yet. They are said but not published. So we've been observing the atmosphere of Jupiter since decades. This is actually a movie shown like film. And we know that Jupiter has these wings, these jet streams, but we don't know how deep they go into the planet. And this is really a question that matters a lot, because all the models that I showed before are made assuming that the planet rotates at a digit volume. And if it happens that these wings go very deep into the interior, then there will be a lot of mass involved. And of course, they are going to have an effect on the gravitational moment. So then we will have to change our calculations. And that's why we started to wondering about this, about the calculation of the atmosphere, about how deep these wings were going into the planet. So this is the same figure I showed before, J4, J6, these are all our calculations, this is the Juno measurement. And the question is, okay, all these models are made assuming a rigid volume, and we found one that fits Juno. But what happens if those wings go all the way to the center of the planet? So then we did the calculation, and what we found is that the moments in this area here can actually match zero with us if we consider differential rotation. For example, if we take this moment here that clearly are not fitting the zero point, well, if we take into account the differential rotation, then they might fit zero as well. So for us, it works effectively as an increasing of the error bars, let's say, for our moment. So, well, we said, okay, this is pretty neat. We really need to further solve this. We want to know exactly how deep these things go, and then we will know more about which interior models actually work for doing that. So then we started wondering the best way to do it. And as I said at the beginning, I hope you remember, the J4 examples are actually giving us more information about data. Data systems. So first of all, why am I giving this talk? Well, I guess the truth was coming back very recently from a meeting at the United Nations in Vienna, where I was rather happy having achieved a pretty important milestone for data interoperability in astronomy. So I came here and I was telling some colleagues about it, and the response was, why are you bothering? So that's what I'm still involved with that crap? Yeah, fair enough. So what is the perception? Well, the perception is a failed experiment. There is no progress, there is no benefit for the astronomers. As an insider, I know that it's overall successful, that the IOA infrastructure is implemented in major data centers and is being adopted by new major projects. There are plenty of hidden benefits to astronomers, and there are also some visible benefits but not recognized as such associated with the GEO. And a couple of words about the hidden GEO here. So anytime you access nowadays a major astronomy archive, you are using the Virtual Observatory. And more new data products and databases are produced by pipelines and software which includes all the GEO standards of GEO nature. The use of GEO standards fosters the use of archival data, and one of the reasons is that the user community, or even archive, is not the user community that's wavelength or a particular science project, but it's not the old expert community, but it's community, people that come in, astronomers that come in from different places by using the Virtual Observatory interfaces. And this has been seen by NASA, the NASA archives, now they're called NASA GEO, NAVO, and they finally, in the last couple of years, have implemented all of these interfaces, and they've noticed quite a rise in the user base. It also fosters interoperability between data acquisition tools, and more of this we'll be talking about later. And finally, it reduces costs, because once we have these standards, once we can reuse software, once we can do things in a more cooperative way, which is happening, maybe there will be some savings, and so there's more money for financing your science project. So yes, that's a good reason to like this. Now, before we go on, I should define what is the International Virtual Observatory Alliance and the IOA. This is the standard organization for archive management, good archive management, and interoperability of astronomy data and tools. And the VO, the Virtual Observatory, is built on the standards of the IOA. So baseline, let me give you a bit of history. Here's a timeline of data access and interoperability. We start from the 1960s. That's the beginning of computer connectivity from government ARPANET, when we became the internet. 1970 we had mail. That was started within the ARPANET community by producing standards for encoding messages.
最後野沢黒さんの最後クラスの20、30人で益子さんが企画した。
concept of data access in interoperability, that is in science, but not just in science, also society at large, as a way of using and reusing the government data. And for example, here, this is what our government and the part of this community has produced. In that decade, is a report called the Harnessing Our Digital Data for Science and Society. You might look at it and you'll find some concepts that's now pretty normal. And now, in this decade, there is the growth of societal data interoperability projects. And in particular, this idea of the fair data principles that kind of been encoded, that data, especially public data, should be findable, accessible, interoperable, and reusable. Now, what about us? Astronomers have been early adopters of this development, and in some cases we even began for that. For example, email. Well, yes, by using email as soon as it was there. The web, yeah, we have data services. There was soon implemented, like I I'm sure you all use those. It came out in that decade as well, as a transfer protocol between child standards. And the NASA data infrastructure, this is one management, but it's something we use every day. So the fact that now there are wavelength archives, the mission center, mission archives, like our standard archive, that was all set up in that decade. And we were positive. In 1990, we have ADS started here, so access to the literature and the first data links between data and literature. So in the year 2000, that decade was the beginning of the Virtual Observatory, which is just kind of the next step in that progression. So the idea here is to give easy generalized access to data and with that, foster data reuse and interoperability. And there have been a bunch of national projects that work on this Virtual Observatory, one here in the United States, and there's a coordination, an international committee that coordinates these efforts, the IDIA, of which I'm presently the chair of the executive committee. Now, there's been an explosion of more initiatives, especially in Europe, where they get good funding by the government. And the United Nations has realized that this is an opportunity for them, and they're now trying to foster a new project, which they call Open Universe. So So beginning a conference at LISO in 2002, this was the formal beginning. We started a bit earlier than that, and you can see some of the faces that you probably know. Here's Bob Hanish, that's me when my hair was dark, and so that was the formal beginning of this IDOA and the work in the standards for the deal. Now, the IDOA has been promoted by the International Astronomical Union, the IAU, as the official standards organization for fair data in astrophysics, and the United Nations Committee on the Faithful Uses of Other States, OPOS, is recognizing the role of the IDOA as we speak, and this is Open Universe United Nations initiative, which is under approval, and if it comes to be, will be based on IDOA standards and done in close collaboration with the IDOA and its members. And just to show you that some of this is real, this is a snapshot from the meetings in the fall in Vienna, the United Nations, at the United Nations building, and that's a panel discussion including the Secretary General of the IAU, Gil Benvenuti, that's me, and here we have Jared Evans of the Chandra X-ray Center explaining to people at the United Nations how the Chandra Cross Catalog is just a good example of data reuse and interoperability. So what is the virtual observatory? And as Alisa said, the virtual observatory? Well, first let me tell you what it is not. Things it is not. So the VR is not a killer application. It's not a strange portal for a different reality. And this is what lots of people thought the VR would be. Something that solves all the problems, makes everything easy to use, everything transparent. Well, that's not real life. What the VR is, well, there are different ways of killing the cat. One definition is from the point of view of the profession that does research in astronomy, maybe that the virtual observatory is a multi-wavelength digital sky that can be searched, visualized, and analyzed in a new and innovative way. And this is, for example, a definition that NASA likes. From the point of view of the data provider in astronomy, well, the VR is just the latest stage of good data practices in astronomy. So if you take a historical view, we began with each data center or archive having different file structures, when the idea of metadata came to be, different metadata organizational tables. So we have the data. The data is there, taken care of, but it takes work to access it, especially if several data sets are used together. So if you want to do work in X-rays, but you're a radio astronomer, you better learn those interfaces, etc., etc. Now, since it was invented to provide us the destination for moving data files, what the virtual observatory is the next step in this progression towards interoperability of now data services and tools. A way I like to look at this is this kind of three-pronged diagram that at the end will produce new science, and we already have examples of new science coming with it. So the first circle there is data management and access. And we know, and we have demonstrated here in the Chandra Data Center, Data Archive, Space Telescope, of the NASA Archive, TISO, etc., that easy data access in well-managed archive fosters data reuse, new science, and public awareness. In Chandra, we have shown this very clearly with a great diagram that was invented by Arnold Roach and Sherry, and here it is. This is for the Chandra data. You see here the years in the archive, and over there is the percentage of exposure time that's been published in each GSA. And so what you see that in red is the data that's been published once. Some data has not been published, but most of the data, 60% from year 14 of Chandra, is being published at least 3 times, more than 3 times. So this is very easy to use. Now, the other thing, interoperability. And here we're talking interoperability between data, tools, and literature. So this, in a way, is Alisa's idea of a flexible analysis environment that puts data, tools, and literature together seamlessly at the astronomer's fingertips. I'm going to come back to this. And here the third point is looking at the future, or the near future, almost the present, the expanding data volume, the big data. And that means that data is becoming so big that cannot go to the astronomer. The astronomer has to go to the data. So we need workspaces, we need collaboration tools, we also need data mining tools and services to make sense of what this data contains. All of this fits very well in the current scientific data management landscape that is encoded in the FAIR principle. This is, for example, a paper in Nature where there are publications where this concept is exposed. So the idea here that data needs to be findable. So the metadata and data assigned a global unique persistent identifier has to be accessible. And this is done by retrieving the data by this identifier and standardized communication protocols. And then has to be interoperable and reusable. And if you look at the DO, RDO, all of this is there. Now, the DO, in fact, is technically speaking a framework. It's a framework for the archives to organize access to the astronomical data holdings in a way that's commonly agreed and shared data structures and according to a defined data model. It's a lot of the work that took years in the IDI was to define this data model. In this framework, software providers offer a variety of compatible analysis and visualization tools and user interface using the standard. And data centers can provide operating data services. And why do we do this? Because there are clear benefits for science. If you think of some, for example, in supporting interdisciplinary, multi-wavelength, and collaborative research in astronomy, the clear one, exploring the full power of growing and new energy-based large data sets, and also providing powerful and unique data tools for education and public outreach. And this is in fact the aspect that the IAU and the United Nations are more interested about. How do we achieve all this wonderful stuff? Well, we need standards. And that's what the IDOA does. So the IDOA has developed over the years that local standards, if you go to the webpage, which is not a great webpage, you can find them there. So there are standards to find data sets. There are standards for accessing, selecting, and extracting data from the archive. Standards that make possible seamless analysis. And visualization standards, these are among the latest, that open up a whole new world of data exploration. Today, the IDOA is, as I said, was started in 2002. Today, there are 21 member projects all over the world. And one thing to remember is that the IDOA as such has no direct funding. So each affiliated project has to find the money for whatever they do in the deal. And they have to go to the national agencies. And this means that some people have come, some people have gone. But overall, right now, well, it helps. This is where all the projects are. And as you can see, there is a big cluster in Europe. And they asked me about that. How do we do business? Well, most of the business happens online, but there are 2 formalized meetings per year where people get together, working meetings, people get together and finalize the standards, get approval, and move on. And definitely were attended, that's the number of people attending each meeting, and the last one we had, which was in Chile, 151 participants from a large crowd from the southern hemisphere. Now, I'm going to show you an organization chart. That's not because I want to bore you out of a head, but because for this type of setup an organization to work, and this is something that we learned the hard way, you really need to have a very good management structure, very formal interfaces. Because I mean, how do you get all these people from all over the world to work in unison? So this is the organization chart. There is an executive committee, which is the group that has the representatives from the various national groups and projects, and kind of the operations management, and I'm the chair of this here. An important committee that reports to the executive is the Committee for Science Priority, and that's the formalized interface with the science community. And for example, what this committee does, it looks at new project engagement in the IDOA. A job of this committee is to look at the new project, the emerging project, and see, ask them, what do you need? What standards do we have to develop? So to identify the fast-track standards, we did this, for example, for ALMA, developing data sheets. And one way to do this is to organize focus sessions like the one that was organized at the Cape Town meeting in May 2016. I think it's time for another one coming. Then you can see the list here. These are really big projects all over the world that can talk to discuss and we're working with. One of these projects is the LSFC, and the slide is from the latest document, the LSFC Science Platform that was developed for the Science Advisory Committee meeting of the LSFC this past September. And this identifies three major science platforms by which the users can interface with the data and do the science. And one of these three major forms is indeed the IDI with remote user computing and the APIs and software tools. So if we go back to the organization chart, we have working groups, so the technical working groups, software engineers, quite a few people from here participate, and they do, and also data scientists, and they develop the standards. That's where all the discussion and work occurs. And on the other side here, there are the interest groups, and these are kind of science support groups. It's a discussion of scientific needs and requirements and input to the technical working group. In a way, and maybe that's not probably a case, it echoes very much the structure of the standard data science. It's a working model. One box I want to point out here is the education group, because it might be of interest to some people here. Now, a collaboration with the IAU, in fact, at the coming Vienna meeting next summer, there will be a joint session IAU on education. As I said already, there's a possible future involvement at the United Nations level. And one recent driver is to try to set up regional centers that then can collaborate with the IDOA and the IAU at this level. And this is happening kind of slowly. I don't think in this country we're already there. One of the problems with the United States is that we're so big and we have a tradition of not working together. So it's continuous. Now let's talk about problem areas. So the real, I think I already alluded at this. One problem is bad communication. People didn't know what was happening within the IDOA. We're trying to remedy that. There is now a formal media group. We'll be designing the web page so people can really get access easily to all the standards, to the various data in the various archives, and also the video-enabled tools.
なるほど。ここに泊まれるじゃないですか。
I think when you know how difficult it was going to be to produce some of these standards and software tools based on that, so that led really some jarring with the community, and most of that was the wrong perception of the nature of the VO, which, as I said before, is definitely not stiff, but what it is it is. I think Rio, at least how we understand it now, is a better metaphor is definitely evolving ecosystem. So that the IDOA has the role of defining the standards for interoperability and data management.
うわ、熱っ。逆に風邪ひきそうだ。これ入らないといけないかもしれない。ちょっと風邪ひきそうだな。逆に。
Let me talk about some of the successes. One very remarkable success, I think, is that we have archives in the Special Observatory. All the major astronomical data collections are now accessible to the Earth. And here a list of archives, multi-wavelengths in the States, in Europe, in Canada, etc. So if you get data from any of these archives, and this is likely that happens, you're using the Earth. NASA, for example, has implemented IDOA standards across distributed archives and over chain of data over 15 decades of frequency. They're very proud of that. They go from the infrared to the gamma rays. And they see that the real services are now widely used to access their archives, which are now called NASA Special Observatories. That's a plot they give. In several cases, LEO is now part of the infrastructure of the data centers and the pipelines and their archives. And for example, the Canadian archive is built around LEO standards, and they're also producing the standards. In Europe, the Gaia and Euclid data centers are also based and Captain INTA is making use of these standards. And this is a way, and it's very clear that INTA uses this because of the economic appeal. They can use concepts like they even can use software, and that makes all their operations easier and smoother. And now we go to the seamless science, which is this new paradigm for research that Alyssa has been talking about for quite a while, and this is a picture that I stole and Fox's Alyssa here a few years ago, where you have this idea that the researcher sits between tools, or software, and then there is the data, and then there is the literature, and the idea is that you're sitting there, you should be able to do it all in one session, without logging in, trying to do different things. Concentrate on science. So, this is now can be done with the integrated archive literature analysis session. And this can be done because we have IDOA compliance user interfaces, we have IDOA created protocols, we have SAMP, which is a communication mechanism that makes various software tools talk to each other and talk to the new archive, and also ADS, which under we have archive data literature links, and that probably will be expanded in somewhere in the future. There is a growing set of software tools, applications that are LEO compatible. And here's an example, and I'm pretty sure that you know at least some of them. Some of you might have used DS9, doing the local thing. Perhaps some of you have used the Aladdin interface. And TopCat is something that lots of people now, especially younger people, of course, with survey data, etc., use quite a bit. And you might use these, and you might not know that they are LEO tools, but they are. Now, here I want to give a particular demonstration of how this works. And this is something that, for example, you can do as an example of comparing data that you may have with the Chandra Source catalog, finding if some of your sources have X-ray counterparts, and then choosing interesting objects for further analysis. That's a typical working data science session. Now, this can happen because we have the LEO data archive, TopCat, DS9, the Chandra interface, Sherpa, and even Python, all parts of the LEO family. And this includes the use of a bunch of IDOA standards that are listed there.